Okay, so now we turn to the proof of the theorem 1.4.3 is the density of set of rational numbers in R. And what does it say? So it says that for every two real numbers A and B with A less than B, there exists a rational number satisfying that is a rational number R satisfying R sits in between A and B. Before actually looking at the proof, the point is the following. So this is the real line. So this is 0. Suppose you have a number B, strictly bigger than, say, a number A. So if at some point you divide the real line into really small pieces, so something like this, and you take steps of this size, at some point you're going to get really close to this number A here, and when you move over you're going to land inside, because if not you will require to take a step that is too big to go over B, I mean to land on the other side of B. So provided you divide the real line into really small pieces, I mean so really small intervals, if you take steps of size 1 over n for a really large n, at some point you're gonna need to land somewhere in here. And m, I mean so if you the number of the steps you take will be m, and the size of this small thing will be 1 over n. So the size of the really small interval here will be 1 over n. And that will be a rational number, m over n, where m is the number of steps you take to get inside in between A and B, and A at the interval A comma B, the open set the open interval A comma B, and n is just the size of this really small interval, so the step size. Because why? Well, m is a natural number and n is a natural number as well. The existence of such an n will be guaranteed by the Archimedean property, and so will the existence of m, which is a consequence of one of the problems that we had the last problem session, problem solving session. Okay, so proof. Irrational number is a quotient of integers, right? So this is the first thing. Did you notice the they point out in the book. So rational numbers are quotient of integers. So what we need to find, m in z and n in n. M here is what we care as a sign. So before in this drawing, I was just considering only positive numbers because I mean everything is actually works the same way if we are over here. So there's no loss of generality in that. So we need to find m in z and n in n such that so that what happens? A is smaller than m over n, which is smaller than b. And as we said, the first step is to choose n. Choose n. So how small do we want? I mean, how big do we want n to be? So we want this width to be larger than 1 over n. So we want 1 over n to be smaller than b minus a. But how do we know such an n exists? How do we know such an n exists? Well, we know by the second part of the Archimedean property here that if y is greater than 0, then there is an y is greater than 0, there is an n in n such that 1 over n is smaller than y. What is this y greater than 0 that we need in here? That's b minus a. So by the Archimedean property part 2i, since y equals b minus a is greater than 0, we know there is such a number n in n. Right, and how do we know that b minus a is positive? Well, these are the two endpoints of an interval, and we need to have b to be bigger than a. So b minus a is going to be greater than 0, just by the statement of the theorem. So we're already assuming that. So we have an interval that's well defined. So one of the endpoints is b and the other one is a. Sorry about that. So b is greater than a, because b is the rightmost number. So it's the endpoint, and A is the lowest endpoint in the interval. B is the bigger number of the two. And so we know that there's a number n, such a 1 over n is going to be smaller than b minus a. Okay, so that's one part. So now we need to choose m, and so we choose. No. We need to find m in Z. Okay, so what exactly do we need? So if we need, we need to find m in Z such that a is less than m and m over n is less than b. Remember here that n is already known to us. I mean, we already chose it. Okay. So we will multiply this thing on all sides by n. Remember, n is positive, so we're not going to change the inequalities here. We're not going to reverse the order of these inequalities. So if a is less than m over n, then multiplying by n is not going to change the sign here. It's not going to be flipped pointing the other direction. So na is less than m, and then if we're multiplying by n on all sides, we get b n or nb. So these two statements are equivalent, or you can go from one to the other by multiplying or dividing by n. So this is what we want to have. If we find a number m that sits between na and nb, we'll be done. So we actually want to pick the smallest number m that is bigger than na. So we pick m in Z. So that a minus 1 is smaller than na, but m is strictly bigger than na. So it's the smallest number that surpasses an a. So if you try with m minus 1, you would fail. So m is the first time that you, it's the first number that, first z in C that is bigger than n times a. How do we know that we can find such an m? Think about the last problem in the last problem session, and you will see that this is how, this is how we can obtain such an m. Now, let's notice here that from this inequality, actually, so if we look at this inequality here, and we divide by n on both sides, we get that a is smaller than m over n. We want to find rational numbers between a and b. So now we've found one that is bigger than a. Well, that's no challenge. So the point here is to prove that this m over n is actually smaller than b. Now remember, recall that we have this inequality here. So we chose n, We chose n already, so that this would hold. And this implies actually that b minus a, if you move 1 over n to this side and a to the other side, we get that a is actually smaller than b minus 1 over n. We know, on the other hand, that 1 over n is less than b minus a, or was the same that a is smaller than b minus 1 over n. And we already know that also because of this inequality, and that m is less than or equal to na plus 1. Okay, but na is less than what? If you multiply this by n, we get that na is less than, remember n is positive, this is less than n times b minus 1 over n, which is, if we distribute this, will give us nb minus 1. So this is smaller than, we can plug this in here. Well, we can plug this in here, well, instead of that, because that bounces na from above. So you get nb minus 1, and then plus this 1 over here, and this minus 1 and 1 cancel out, and this gives us nb. Right, so this is, so we have then that so we also know that m is less. In fact, well, this inequality here is strict. Remember that na is strictly smaller than n. Na is strictly smaller than nb minus 1. This implies that m is strictly smaller than n times b. And here, if we divide by n on both sides, we get that m over n is less than b. But combining this and this, we get the desired, the existence of the desired rational. Okay, so that's a proof of the of why Q is dense in R. And in fact, it is given to you as a corollary. Okay, so this statement is about the rational numbers. So rational numbers are dense, which is kind of the hard part. I mean, showing that a much smaller set than R is dense in R is much harder than to actually showing that they're irrational numbers, or at least it is what you expect. I mean, the really tiny set of rational numbers is dense in R, then you certainly expect that of the of the irrational numbers, since there are way more of them. So there's a corollary here. To corollary 1.4.4. Given any two real numbers A smaller than B, there exists an irrational number T satisfying A is less than T is less than B. And the proof is left to you as an exercise. It's actually part of one of the exercises of the section. But of course, I mean, as I said, once you know that the rational numbers are dense, then you certainly expect that the rational numbers will be dense in R. So if the rational numbers are dense in R, then you certainly expect that to be the case for the irrational numbers. Okay, this is one of the exercises at the end of the section. Okay, now we'll move on to the existence of square roots, which is something we anticipated long ago. And we actually performed some of the computations that are going to be involved now in this part of the analysis. And like I said, I mean, this is something we already mentioned, or we already implicitly used. I mean, we already used the Archimedean property. It's just we didn't know it back then. Okay, so let's move on to this new theorem. It shows that we anticipated the cut that corresponds to the square root 2 is again the set of rational numbers such that t squared is less than 2. So in fact, we're going to define the square root of 2 as a supremum of the set of real numbers now, such that the t squared, so the real numbers t, such that t squared is less than 2. We'll show that t, that set t, must be bounded from above, and therefore it has a supremum, and then we'll show by hand that the supremum must satisfy that it is equal to 2. We know the supremum exists because we're in R, and so it satisfies the least upper bound property. Now we'll show that supremum squared is equal to 2, and therefore that's what we call the square root 2. Because if we assume that, I mean, there are three possibilities: either that number, the supremum squared is less than 2, then it can also be greater than 2, and the only other possibility is it's actually equal to 2. If supremum squared is less than 2, we'll see that in fact that number cannot even be an upper bound, so we were not actually dealing with a supremum to begin with. If it is strictly bigger than 2, then it's not going to be the smallest of the least upper bound. So we'll find an upper bound to the set that is still yes, that is smaller than this other upper bound. Okay, so supremum squared cannot be greater than 2 again, because we can put a number in between that number and the set of real numbers such that their squares are less than 2, and therefore we would be violating the property of being the least upper bound. So this is what we're going to do then more rigorously next time, in the next video.